After years of continuous breakthroughs in quantum computing, Google has unveiled a revolutionary quantum computing chip called Willow. This innovation marks a transformative moment in the field of computation, introducing precision, scalability, and reliability that could reshape how we approach some of the world's most complex problems. Willow not only addresses long standing challenges in quantum systems, but also opens the door to incredible advancements in artificial intelligence. As we stand at the precipice of this technological leap, the question arises: how far can AI go when powered by quantum computing? And are we ready for what lies ahead? To understand Willow's significance, it's essential to revisit the foundations of quantum computing. Unlike classical computers, which operate using bits that represents either 0 or 1, quantum computers use qubits. Qubits can exist as 0, a 1, or both simultaneously thanks to a property called superposition. Additionally, qubits can exhibit quantum entanglement, a phenomenon where qubits are interconnected in such a way that the state of one qubit instantly affects another, regardless of the distance. These two principles enable quantum computers to process information in fundamentally different and exponentially more powerful ways than traditional computers. However, despite their potential, quantum computers have historically faced a significant obstacles. Errors. Qubits are notoriously delicate and easily disturbed by their environment, which causes them to lose the information they store. This issue, known as decoherence, becomes more severe as the number of qubits in a system increases. As a result, scaling systems to handle practical, large-scale problems has remained an enormous challenge until now. Willow is a groundbreaking step forward in overcoming this hurdle. Google's latest chip demonstrates a critical advancement below threshold error rates. In simpler terms, as more qubits added to the system, the rate of errors does not spiral out of control. Instead, it decreases exponentially. This achievement is monumental because it proves that quantum error correction, a concept first introduced by Peter Shor in 1995, is now viable on a large scale. The development process behind Willow highlights the rigorous efforts undertaken to achieve this milestone. Researchers began by scaling up small arrays of qubits, starting with 3 by 3 grid, then progressing to 5 by 5 and eventually a 7 by 7 configuration. At each stage, Willow cut the error rates in half. This exponential reduction is a significant indicator that quantum error correction isn't just theoretical but achievable in real-world applications. Moreover, Willow is the first quantum chip to demonstrate real-time error correction, extending the usable lifetime of qubit arrays far beyond that individual qubits. This makes Willow the most convincing prototype of a scalable logical qubit ever created. Willow's performance is unprecedented, setting a new benchmark in the quantum computing landscape. Google put the chip to the test using the process called the Random Circuit Sampling or RCS test. This computation measures whether a quantum system can outperform even the fastest classical supercomputers. Willow completed the task in under 5 minutes, a feat that would take today's most advanced classical supercomputer, such as Frontier, an estimated 10 septillion years. To put this into perspective, a 10 septillion years is more than a trillion times as the current age of the universe. Even under ideal conditions for classical systems, Willow's quantum capabilities eclipse them by an astronomical margin. This achievement highlights an ever-widening performance gap between classical and quantum systems, growing at a double exponential rate. While Willow's speeds and error correction are groundbreaking, the implications extend far beyond benchmarks. Hartmut Niven, the founder of Google Quantum AI, introduced an intriguing idea. Willow's unprecedented performance might be explained by quantum computation occurring across multiple parallel universes. This concept draws on the multiverse theory proposed by physicist David Deutsch. Although speculative, it's a fascinating way to think about the scale and potential of quantum mechanics. Whether or not the multiverse interpretation is accurate, Willow provides a glimpse into a computational future that defies traditional limits. Beyond theoretical achievements, Willow sets the stage for real-world applications that could revolutionize entire industries. Historically, quantum computing experiments have fallen into two categories: performance benchmarks like RCS, which lack immediate practical use, and simulations of quantum systems, which classical computers can still manage in limited cases. Willow changes this dynamic by demonstrating that scalable, error-corrected quantum systems are within reach. The next major milestone for quantum computing is achieving computations that are both beyond the capabilities of classical systems and directly impactful in solving real-world problems. Fields such as medicine, energy, and material science are poised to benefit tremendously from this leap. For instance, quantum systems could be used to design new drugs by simulating molecular interactions at a level of detail that classical computers cannot achieve. Similarly, quantum computing could accelerate the design of more efficient batteries, help optimize renewable energy systems, and unlock breakthroughs in fusion energy, a goal that has eluded scientists for decades. These are complex problems that traditional computers struggle with, but quantum systems like Willow have the potential to solve them with ease. The correction of Willow wasn't just about adding more qubits to the system. The chip was developed in Google's state-of-the-art quantum fabrication facility in Santa Barbara, one of only a handful of such facilities worldwide. Every aspect of Willow's design, from its architecture to its gates and readout mechanisms, was carefully optimized to ensure seamless functionality. Willow's qubits exhibit a coherence time, the length of time they can maintain quantum information of nearly 100 microseconds, a five-fold improvement over previous quantum systems. This focus on the quality of components rather than sheer quantity ensures the chip delivers reliable, scalable performance. Perhaps the most exciting implications of Willow's development lies in its synergy with artificial intelligence. Quantum computing and AR are two of the most transformative technologies of our time, and their combination could unlock unprecedented possibilities. Quantum system could accelerate AI training processes, optimize algorithms that are too complex for classical computers, and analyze massive datasets with unparalleled speed. This synergy has the potential to drive breakthroughs in scientific research, autonomous systems, renewable energy, and countless other fields. The announcement of Willow had immediate ripple effects beyond the scientific community. Following Google's reveal, Alphabet's stock surged by 5% as investors recognized the transformative potential of this breakthrough. Competitors like Microsoft and IBM are also racing to achieve commercially viable quantum systems, but Willow's success sets a new benchmark for the industry. It demonstrates the long-pursued goals of scalable system and effective error correction are no longer just theoretical but achievable realities. Despite Willow's remarkable achievements, there is still a long journey ahead. The next challenge is bridging the gap between experimental quantum demonstrations and practical, real-world applications. Google's roadmap includes milestones such as achieving a beyond classical computation, one that solves a real-world problem more effectively than any classical system. To accelerate this progress, Google is fostering collaboration by sharing open-source tools and educational resources, including a new course on quantum error correction available on Coursera. By inviting researchers and developers to contribute, Google hopes to build a broader community that can tackle the challenges of the future together. Willow's development marks a turning point for quantum computing. It is not merely a milestone, but a clear signal of the profound impact of this technology could have on science, industry, and innovation. From advancing AI to solving some of the most complex problems in medicine, energy, and beyond, quantum computing is poised to drive transformational change. As we inch closer to a future where quantum systems play a central role in computation, one thing is certain: the breakthroughs we've been waiting for are now within reach. This achievement raises both hope and caution. On the one hand, technologies like Willow promise to solve problems that were once unmanageable, pushing the boundaries of what is possible. On the other, they prompt questions about the implications of machines that surpass limits we never thought achievable. Are we prepared for the power and responsibility that come with quantum computing? As we look toward the future, one thing is clear: the journey has only just begun and the possibilities are limitless.